Okay, so today's video is going to be looking at rates of reaction, and it's going to be looking at the content that you've got to be aware of and you've got to understand inside the National 5 chemistry course. Okay. So our learning intentions are that you're going to be able to understand the importance of reaction rate inside chemistry. You're going to be able to explain how the average reaction rate can be measured, and you should be able to correctly calculate the average reaction rate using information that is given to you, and the success criteria mirror the learning intentions. Okay. Right, so I'd like you to pause the video for 2 minutes and see if you can use the periodic table to name the elements or find out their chemical symbol. Okay, so pause the video and see how many of these you can work out in the next 2 minutes. Okay, so if you have a look at the description below the video, you will see all of the answers to the starter question that we have here. Okay, the ones that I want to note that are quite interesting are tin. The chemical symbol for tin is SN, and Hg is the chemical symbol for mercury. Okay, the rest of the answers are in the description below the video. Okay, so take a look at them, make sure you got them all okay. Okay, so what is reaction rate and why is it important? Well, the rate of a reaction is the measure of how fast the reaction happens. The faster the reaction, the higher the rate. Okay. Reaction rate is important inside the chemical industry because it has a direct contribution towards how long it takes to make a chemical or compound. So what I'm basically saying is that rate is really important because it has an effect on the amount of time and also how economically viable it is to make compounds. Okay, so industrial chemists, when they are looking to make a reaction, to make a specific compound, they've got to find the most economical way to do this. And the things that they will look at are the cost of reactants, the availability of the reactants that they want to use, and the energy that's going to be needed for the reaction to take place. But they will also look at the rate of the reaction, because if the reaction is really slow and it takes a number of days, then that's going to put the cost up significantly, because you've got to pay the staff to man the reaction, you've got to pay for the facility, you've got to pay for the energy that facility is going to use. There's all of these other things that they've got to take into account. So you want, ideally, my reaction that is going to be cost effective, and that essentially means that the cost of the reactants is low or is reasonable. The availability of the reactants is reasonable. The energy required is reasonable, and the amount of time that it takes for the reaction to happen is reasonable. It's quite low, and that's what you're looking for. So you don't want a reaction that takes 2 or 3 weeks. You want a reaction that you can do in the space of a day, or more ideally much faster than that. So that's why we've got to look at a reaction rate. That's why it's really important. Okay, so factors that affect the rate of a reaction. So the rate of a reaction can be controlled or changed by altering certain variables, and the 4 variables that I'm going to outline shortly are the variables that are able to control the rate of a reaction. And these are the ones that you've got to be aware of inside of the National 5 chemistry course. Okay, so the rate of a reaction can be increased by all of the following. So if you increase the concentration of a reactant, this means that there are more reactants inside of the reaction mixture, and therefore there's a higher chance of a successful collision and a reaction taking place. If you decrease the particle size of a reactant, this is going to mean that you've got a larger surface area, and therefore again it is a higher chance of a successful collision. If you were to increase the temperature of the reactants, this is going to mean that the reactants have got a higher average kinetic energy and therefore collide more frequently. They get with higher energy, and this is going to make the reaction faster. And the final one that you've got to be aware of is if you add a catalyst, this lowers the activation energy and is able to provide you with an alternative reaction pathway. Okay, so that's the 4 factors that you've got to be aware of that are able to increase the rate of reaction. Okay, so I've got a couple of examples here of fast and slow reactions. So the reaction of methane gas with oxygen is extremely quick, and it's got a high rate of reaction, and this reaction is obviously explosive and it's extremely violent in nature. And the picture that I've got here is actually a relatively recent picture. It was taken in November 2019. It's a chemical plant in Texas. There was an explosion, and unfortunately 3 of the plant workers were actually hurt. No one was killed, which is good, but 3 people were injured, and this is what can happen if you have a runaway reaction, or the rate of a reaction is too high. It can obviously release a lot of energy and cause an explosion. And this is another example of a reaction. This is the reaction of iron with oxygen. And this is just essentially rust on a car. And this is a really slow reaction, and it's got a low rate of reaction. Okay, this is something that you don't want to see. Rust on the body of your car, this is not good. Okay, so a little task for you. Can you think of any other reactions? Are they fast or slow? Okay, that's something that you can try on the side. So that's us ticked off the first learning intention and the first success criteria. You should now be able to understand the importance of a reaction rate inside chemistry. Okay. So how can the average rate of a reaction be measured? Well, the average rate of a chemical reaction is the change in the quantity of a reactant or product over time, and can be calculated using data collected from experiments. Okay, and the equation that you want to be using is average rate of a reaction is equal to change in quantity over the time taken for that change. Okay, and there are 3 types of experiment that are looked at in the National Chemistry course, the National 5 chemistry course. And these are measuring the change in volume of a gas produced, measuring the loss in mass during a reaction, and the final one is measuring the change in concentration during reaction. Okay, so I'm going to go over all three of these, and then we're going to look at a couple of graphs, and we're going to look at how you would actually calculate the rate of a reaction and what the units would be. Okay, so example number one then is measuring the change in volume of gas produced. So in a reaction where a gas is produced, if a gas can be collected and measured at regular time intervals, okay, and we've got a setup here where we have a measuring cylinder, and we're collecting the gas in here that's going to be made from our reaction. If the gas is made in here, it moves all the way up through the tube into the measuring cylinder, where we're able to measure how much gas is being made at regular intervals. Okay, and the reaction that we're going to be doing to demonstrate this is calcium carbonate reacting with hydrochloric acid. Now, this reaction makes calcium chloride, water, and carbon dioxide. And you can see this is our carbon dioxide being made in the reaction over here, and then it's moving all the way along, and it's getting collected inside of the measuring cylinder. And what we do is we measure the volume made over time, and then we take a note of that, and we plot a suitable graph. Okay, so that's one example of how you could, in theory, measure the rate of a reaction. Okay, and it's only applies to reactions where a gas is being made. Okay, another alternative setup that I do want to mention that's probably a little bit more accurate is if you were to attach a gas syringe on the end of this and let that fill up over time. That would probably give you a more accurate picture of what's being produced. Okay, so the second type of reaction that you've got to be aware of, and the second method for measuring the reaction, is looking at the loss in mass. So if we take the same reaction that we were just speaking about in the first example there, calcium carbonate reacting with hydrochloric acid, making calcium chloride, water, and carbon dioxide. And if we set it up differently, where we have our hydrochloric acid inside of a beaker that is just open to the atmosphere, and we put this on a scale or a balance, then you could, at regular time intervals, measure the total mass of the beaker, and over time you should see that the mass overall is going to lower, it's going to decrease. Okay, and this is obviously because the carbon dioxide that's being made in the reaction is being lost to the atmosphere. So therefore, the mass overall of the reaction mixture and the products is lowering, because you're not containing the CO2 that is being made. Okay. So obviously, if the CO2 was being made much faster, then the loss in mass of the vessel overall, it would be much faster. Okay, so this is what it would look like. You would have the beaker on a balance, and you'd want to add in your calcium carbonate into the hydrochloric acid, and then you'd want to, like, every maybe 20 seconds or 30 seconds or so, measure the mass on the balance, and you'll see over time that the mass on the balance again will start to drop. Okay, and this setup can be used to investigate the effect of the particle size of the reactants. It can be used to investigate the effect of the temperature of the hydrochloric acid, and it can also be used to investigate the effect of the concentration of the hydrochloric acid. Okay, on the rate of the reaction, of course. All right. So hopefully that makes sense. So that's the loss in mass examples that you will see in the National 5 chemistry course. And finally, you can also measure the change in concentration during a reaction. Now, I've taken the same example here just to make it a bit easier to follow, but I must stress that the reaction that we're looking at here is not a good example for this, but the principle is the same. So you would start off your reaction, and what will happen is that the acid is going to be neutralized over the course of this reaction, and it's going to be used up. So what you could in theory do is take a sample of your reaction mixture at regular intervals, and test the concentration of the acid straight away, and what you would find is that the concentration of the acid over time is going to be getting lower and lower and lower as it's getting used up. But this method requires a viable titration method to effectively assess this, and you would actually probably want to do a reaction that is much slower, that maybe takes like 3 or 4 hours for it to complete. In that way, you would be able to get good data for this one. So this is not the best example, but I hope that the principle is there. So essentially, you take samples like every minute or two from your reaction mixture, just over a defined time interval, and then you want to measure the concentration of a reactant, and the one that I went for here was hydrochloric acid. Okay, you test the acid concentration. Okay, so that's our second learning intention and success criteria met. So you should now be able to explain a couple of methods of how a reaction rate can be measured. Okay. So how do you actually calculate an average reaction rate from a graph? Okay. So I've got here an example of mass versus time. So a graph plotted from the data obtained by measuring the mass, concentration, or gas volume as they vary with time during a reaction can be used to calculate the average rate. So this graph shows how the mass of a reaction between marble and HCl varies with time. So if you wanted to calculate the average rate during the first 7 minutes, you would first of all have a look at the mass at the start. So the mass at the start was 122.5, and then you would look at the mass after 7 minutes, and you would see that the mass after 7 minutes is 122.32 grams. And what you would do is you would calculate the change in mass, because if you remember all the way back when we spoke about the equation that we're going to use, it's always the change in the quantity over the time interval. So this is what we're doing here. We're saying change in mass. So the change in the mass from the start up until 7 minutes, it was 0.18 grams. Sorry, and then you just divide that by 7, and the units are grams per minute, and that's it. That's you got your average rate over the first 7 minutes. Okay, and I have another example here. So the example that we have here is volume versus time. So you can see that this is also looking at the reaction that we had of the marble and the hydrochloric acid making our CO2. You can see that over time we generated a certain volume of gas. Okay. And they're wanting you to work out the average rate between 10 and 15 minutes. So the change in the volume, so first of all, they're going to be look at what the volume was at 10 minutes. It was 100 centimetres cubed. And then we look at what the volume was at 15 minutes. It was 130 centimetres cubed. So we work out our change in the quantity. So our change in the quantity was 30 centimetres cubed. 30 centimetres cubed of gas was generated over this 5 minute period. And then we put it over the time interval, which was, well, at 10 minutes to 15 minutes is 5 minutes. So therefore, an average rate of a reaction is 30 over 5, 6 centimetres cubed per minute. Okay, the thing I want to touch on is that it's not always going to be in minutes, and it's not always going to be in centimetres cubed. It could be in litres per second, it could be in grams per minute, it could be in grams per second. Just always make sure that you look at the graph and you check what the units are. Okay, so it's always going to be the change in the quantity over the change in the time or the time interval. Just make sure that you check what the units are on the graph, and then that will obviously control what your units are going to be for the average rate. Okay, so that's us met our learning intentions, our final learning intention, I should say. So we should now be able to correctly calculate the average reaction rate using information provided. Okay, and that's us met all of our success criteria, hopefully. Okay, so if this has been any help to you, then please do comment on the video. Please share the video with your friends that are maybe sitting the course. And I'd like to obviously thank the references that I used as well for this. I used the Lecky and Lecky book, and there was also some good sources from a PHS chemistry, which is a high school in Scotland. Okay, so yeah, thank you for listening, and I hope it's helped you. There will be more videos shortly on the channel.